Jamie Lake and Ralf Mountain. And the title of their project is Focal Depth Tracking for Improved Three-Dimensional Holographic Displays. This is a progress report, and the final presentation will be in June. So, Peter?
Cool. Well, in which case, I'll begin. So I'm afraid if you're expecting something exciting today, then you are not in luck, because there isn't much to share, and so, but I'll get to that in a sec. So project title is that focal depth tracking for improved three-dimensional holographic displays. And what that translates to in real terms is eye trackers plus holograms is cool. So who am I? Well, my name is Peter Christopher. I'm a research associate at University of Cambridge. I'm soon to be a research fellow at Emmanuel College, and I'm a co-founder of Exobotics. And my real interest is in all things. Why is this auto-scrolling? My apologies. The best thing about COVID for me is that I don't need to leave my armchair to do a presentation. But I'm actually presenting on the behalf of a bunch of other people who are actually the real heroes here. Can I apologize? This thing is not working as expected. Okay, I'm very sorry. We're having technical difficulties. Okay. All right, my apologies. We'll start again. Hi, I'm Peter. If you can hear me, give me a wave. I'm a research associate at University of Cambridge, soon to be a research fellow at Emmanuel College. I'm also co-founder of a space startup. It's not very exciting, and I like holograms, so that's me. But I'm actually presenting on behalf of a bunch of other people. Yes, behind every mediocre presenter is a team of the actually competent people who do all the good work. So the first is Jamie Lake, who's a PhD student and is project manager. Second is
your presentation, actually.
Oh, sorry. This has been a comedy of errors.
Not to worry.
Okay, does that work now?
Yes, I can see the.
Okay, I blame Microsoft. There's Ralf Mountaan, who's a colleague of mine, and is the optical wizard behind it. There's Hannah Joyce, who's a reader in low-dimensional electronics, and there's Tim Wilkinson, who's a professor of something to do with timey-wimey holographic stuff. No one's really sure what. Unfortunately, I can't tell you anything interesting in this presentation. The first is because of COVID. All our experiments require multiple human participants, which has not been allowed at any point during the COVID. So we have been able to do nothing other than the theoretical back end. And while that's interesting, I can't talk to you about that stuff because we're still in sort of discussions about patents. So I'll very briefly introduce you to some holography, and then I'm afraid I'll have to leave you there because that is all I can say. And before we begin, I owe a shout out to the Observatory for Human Machine Collaboration, which has just started up on main site, because they paid for this beauty here. So this is a state-of-the-art eye tracking unit. It sits in front of your computer. It doesn't look like much, but the price tag says otherwise. And it tracks you around the room in extremely high detail. And then the CAPA award, which we're presenting for here today, is kindly paying for the optical components that go with this. So you've all seen variations on a traditional projector. Your projector shows something on its display or its micro display that looks not too dissimilar from what you eventually see on the screen. It'll be distorted somewhat, there'll be some different contrast and things, but fundamentally it's the same image. Whereas in a holographic projector, you show something that, for all intents and purposes, looks like random noise. And in fact, it's very similar to random noise in many ways. And then the optical setup does a Fourier transform on this to show you a reconstructed image. Now, this has a number of advantages and disadvantages. The big advantage is it allows us to do 3D. Your reconstructed image can be fully 3D, and it can, from your point of view as an observer, be in the room with you. So it's not, doesn't have to be like, I don't know, an Oculus Rift or something where you're showing two flat images to each eye. You could actually see this, you could walk around it, and you would move as you'd expect. And it also solves a number of the problems with sort of current 3D tech. So you want to know more, you're in the right place. So the long-term vision for this is to go from like a handheld projector like this. So this is a small projector. It's actually in front of you here. You're seeing through the glass, and I recommend watching that video if you get a chance. And to go from that to holodeck, so something immersive where you've got holograms on all sides of you. So this is my incredibly bad quality artistic render, but the idea is that the man there in grey sees the man there in blue, and there's an array of projectors behind him projecting that screen. They individual at every angle, and you can see why my career as an artist was cut short. Apologies. And the fundamental technology behind hologram is, these pictures are thanks to Jamie Lake, so I don't want to claim credit for myself, is that you are passing, say, a series of planar wave fronts and behind. So typically that would be a laser, and what we do. You're passing it through a diffraction field, which in this case is a spatial light modulator or equivalent. And then there's a Fourier transform that occurs between that diffraction field to the replay field, is what you see. So the replay field might be, say, a projector screen, or the surface of your glasses, or your eyeball itself. So this is the example you're most likely to see it in at the moment. Is move on to this one. Yes, yeah, your eyes are looking outwards, and at different depth planes, you're seeing different images. And typically nowadays, that's for a headset because of limitations in holographic technology. So these pictures are thanks to Jamie. So this is a good demonstration here of, you can, by scrolling through here, and if you change the focus on your eye, you can choose which one of these objects you want to be in focus. And the key thing there is that on stereoscopic headsets, like say an Oculus Rift, that choice is made for you by the camera operator or the software you're using. Whereas here in a holographic headset, that choice is made for you by you. You can choose whether to focus on at different depth planes. And what we're doing is we're adding eye tracking to this mix. Now, eye tracking has been done before for different elements, including virtual eye boxes and things. We've got a new element that it can be tied to. It has some new algorithms, which I think are interesting, but no one shares my opinion. And there's a bunch of patents in progress. We're in conversations with a couple of companies. We're pursuing licensing. And it's a classic, I'd tell you, but then I'd have to kill you thing. So unfortunately, what I'd like to say here is I have to give you this amazing XKCD cartoon. So it's a new project going forward. I could tell you, but I have to kill you. I mean, kill you even sooner. And that's it. So I'm afraid it's keep calm and ask questions. Thank you very much.
Thank you, Peter, for this very interesting presentation. especially graphics. So please, does anyone has any questions?
It's okay if you don't, because I realize I haven't said anything that most of you probably don't know far more about than I do. So
I have a simple question. Is
yes.
in terms of costs, do you have any estimates of how much it would cost to manufacture these things?
What, the eye tracker or the holographic projector?
The holographic projector.
Varies wildly. So none of the components in the holographic projector are any more expensive than the components in, say, a HoloLens made by Microsoft. They're just used differently. The difficulty is they're not as readily available off the shelf because there isn't alternative markets for them. So everything in a HoloLens, well, almost everything, you could also find in a mobile phone or cinema projector. So that means R&D costs are high, but eventual production costs wouldn't be any higher. One exception to that is that current holographic technology requires massively more computational power than equivalent classical projectors and gives you on a per pixel basis lower image quality. And that's traded off against the fact it gives you full 3D and a bunch of other good things, but it comes at disadvantage of basically it requires more pixels per bit of how good it looks and more computational power. But again, that's stuff that's you can get off the shelf. So development costs are reasonably high, as any kind of research is, but the eventual production costs probably aren't that much higher than the equivalent classical machine.
Okay, thank you.
Side note on the eye trackers are expensive. So the latest generation of headsets are including eye trackers, and they're not that expensive because none of the bits inside an eye tracker are expensive. I mean, I think the most expensive thing is an IR LED, but because they're very low volume products at the moment, are expensive. So that projector I showed you earlier costs best part of 20 grand, and that's not the most expensive one that company sells, and that company isn't the most expensive on the market. But for production, again, the unit cost is probably under £100, which is nothing in the cost of a HoloLens.
The display is based on LCOS?
Yes, our ones, but when for this project, I'm not especially interested in the underlying display. It could be a DMD or something. The technology is about integrating what we know about your eye with the algorithms for showing something. So I use LCOS because I've got a load and they're possibly the most versatile product on the market at the moment. But if the new TI phase devices became available, it could work on that as well. And you could also run it on a TI analog device, amplitude device if you wanted, though you'd get a lot more artifacts.
Okay, next question is, can I imagine like 8K LCOS display being partitioned into like 16 and then giving you on a single plane like 6 full HD holographic display?
Okay, so you've got an 8K HMD, and you're splitting up into 6 regions and then using them all independently as separate displays. Yes,
okay, yeah.
Yes, you could do that. How you'd use it would be a more difficult question. So you could imagine a case where you used a complicated waveguide to combine them to increase the field of view. That's definitely possible. Well, I say it's possible. It's not going to be easy. And I'm not sure it would be the best way to do it. I'd wager quite a bit of money that there were better approaches to that problem. But yeah, you could. I mean, I think probably the more interesting question is, could you do both eyes from the same LCOS device? And the answer to that is very probably. But again, I'd be looking at time multiplexing instead of spatial multiplexing, which is, I think, fundamentally a lot of the problems with the approaches people take to field of view is that whereas classical projectors are very strictly limited on whether a problem is spatial or temporal, that's not true for holograms. The Fourier transform in there means that you can rephrase almost every problem you tackle as either a temporal problem, i.e. summing lots of bad low quality frames together, or multiplexing a spatial problem, i.e. one very good frame. So I'd be looking at that temporarily, using maybe something like a ferroelectric probably for that case, because waveguides are still only average in quality.
Thank you. Does anyone have any more questions? If not, we would like to thank Peter as a speaker. Thank you very much, and best of luck with the rest of your research.
Thank you, and apologies for technical difficulties.
No